Thank you for joining us today for our UV+EB technology webinar series. My name is Jeff Peterson. I'm the publisher of UV+EB Technology, the official publication of RadTech North America. Today, our speaker is Jennifer Heathcote, who's the Vice President of Business Development for GEW, and she will be speaking on how the electrical grid and global sustainability initiatives are triggering a shift to UV LED curing. A very popular topic right now, and I will send it over to Jennifer shortly. One thing I did want to let everybody know is that there is a chat area on the right side of your screen where you can, as Jennifer's doing the presentation, you can put in your questions, and at the end of the presentation, I'll come back on and we will repeat those questions and give Jennifer an opportunity to answer some of those. So, please just do that as you are watching the webinar. I do want to have a quick thank you to GEW for sponsoring our UV+EB technology webinar today. And without any further ado, I am going to send it over to Jennifer. Jennifer.
Thank you very much, Jeff. I am really excited about this topic. This is a topic that I've had a general interest in for all of my career. I had the opportunity to see firsthand in the early days when I got introduced to UV curing about the impact of what manufacturing plants were doing on our equipment. And so I've kind of carried that understanding through my career, and I've often talked about it to many people in the industry. But as long as energy is affordable and energy is reliable and energy is plentiful, a lot of the aspects of the electrical grid just don't resonate. That has changed in recent years. Part of it is that we're all embarking on sustainability goals. Net zero is increasingly part of the conversation. And we're making policy changes that not only are going to have a direct impact on how you run your business, both in terms of your operating costs and the additional resources that you have to put into play, but also your personal life and that of your kids and your grandkids. The decisions we're making today are going to have a direct impact, and not always in a good way, some good, some bad, but they're having a direct impact on how we live our lives over these coming decades. So it's important to understand some basic aspects of the electrical grid and how it affects manufacturing. Some of you may be experts at this. You may know more than what I do, and others may be hearing this for the first time. There's plenty of information in this webinar. I'm going to try to keep it to about 45 minutes and leave some time for questions. But there's plenty of information in here to that those of you who don't have an understanding will learn a ton. And those of you who have maybe a deeper understanding of some of these concepts are going to have a better understanding of how LED is going to help sustainability efforts and also help you reduce operating costs as we go forward. So let me just start advancing through these slides. There we go. So I'm going to start by talking about how we assess unfamiliar technology. And this applies to both LED technology, something that is relatively new. It's been around for about 20 years, so it's not brand new, but for many of you on this webinar, it's still new because you may not be using it and may not be super familiar with it. But we can also apply this to the electrical grid. The electrical grid has been around for well, almost 150, 160, 150 years, a little over 150 years. But many of us, because we don't understand how it works, we kind of take it for granted. So the features of a product are the facts, right? It's what a product is, what it has, and what it does. And we often translate that into benefits, which are the positive effects that you gain by using that product. The challenge we have is when something is unfamiliar, when you just don't have any point of reference, you have no personal experience with it, it's very difficult to assess what the value of adopting that product is. One classic example that's always used is when the iPhone came out in 2007, most of us knew what a cell phone was or a mobile phone, but we really didn't know why we needed a smartphone. And we certainly weren't willing at the time to pay the price for apps and features that we just did not understand how we were going to use. I mean, the concept of being able to send a text message or check your email or check the internet while you were on the go was just not something we valued at the time. Fast forward about 15 years, and now most of us can't imagine living without a smartphone. So the same thing applies to new technology, be it LED technology or something that we're just not familiar with, such as the electrical grid. One thing to pay attention to, though, is that while vendors will often talk about features and benefits, if those features and benefits do not solve a problem, they really don't have much value. They just become nice to have, things that sound good and I would like to have, but I'm not willing to pay for them unless I can directly associate them with solving a problem in my facility. And that value varies. It varies by users. Some users will value certain features and benefits and associate them with a benefit in their production facility, whereas others, don't really need those. So it varies by customer. It varies by application. So we can also take a look at this list of attributes on the left side of this screen to help us quantify that value. In other words, is it something affordable? Is it reliable? Is it versatile? Is it scalable? Does it solve problems or does it create problems? And we can do this with both LED technology as well as the electrical grid. So UV LED suppliers tend to focus on value produced. If you've ever been in a presentation at a conference or had an LED supplier, whether that's an equipment supplier or a formulation supplier visit you, they will often talk about, the ROI, it's affordable, we've come a long ways, it's reliable, it's going to save energy, it's versatile. They'll talk about all those features and tell you the benefits that you're going to achieve. The problem is that the end user is focused on the problems that it's going to create. I mean, it's not uncommon for us to talk to someone who's using UV technology, but is not using LED technology. And all they can think about is the hassles that switching to LED is going to create. I have to switch my formulation. I have to retrain my operator. I have to carry different SKUs. And so the problems in their mind far outweigh any of the benefits that they're going to achieve by switching to LED. And so what we need to do is we need to focus on how the technology solves problems. To be cost effective, value produced, so all the value that's produced from all the features and benefits must be greater than the value consumed. In other words, it has to outweigh any of the hassle or the nightmare that I believe is going to affect my facility if I switch to new technology. And so those of us in the industry have not done a good job framing this to help users understand how LED technology solves problems. And so there's one specific problem that I'm going to focus on today that LED helps us solve, and that is the stress that we are creating on the electrical grid. And for those users that are adopting LED technology, one of the biggest reasons that they then start spreading that technology to more and more presses, more and more lines, and more plants is because they really start to see the value of how LED helps them become more sustainable, helps them lower operating costs, and helps take stress off the grid. And we can apply these same criteria to the electrical grid, right? Right now, everybody is talking about the problems that fossil fuels create. And no one is really talking about all of the problems that reliable, affordable energy have solved over the last 100 plus years. This is a slide just to kind of give you an idea of how electricity generation in 2021 existed throughout the world. So we generated about 28,433 terawatt hours of electricity. And you can see in this chart how that's divided by region. So the bottom dark blue boxes are Europe. The next, going from bottom to top, the next shade of blue is CIS, which is the Commonwealth of Independent States, which is the former Soviet states in Eastern Europe and Asia. We then have North America, which is that teal blue color. And then just above that, a little bit lighter blue is Latin America. Then we go to Asia, and then at the very top, we've got the Pacific, Africa, and the Middle East. So you can see that energy is not really, and this is particularly electrical energy. I'm not really talking about heating and transportation energy. I'm really just focused and narrowing the scope on electricity. But we can see that the energy is not really geographically spread, distributed very well. And of the population, we're about 7.9 billion people globally. And of that, let's say roughly 8 billion people, there are still 3 billion people that have little to no access to electricity. So this chart is only going to grow because in Asia, you've got China, you've got India that are adding more generating capacity, because as we add generating capacity, as we make our grid more stable, the standard of living rises, the GDP rises, the quality of life rises. So electricity is not going to be decreasing. It's going to be increasing for areas of the world that still access on a daily basis less electricity than the average American refrigerator. You know, imagine that. There's 3 billion people in the world that have access to electricity, but it is less than the amount that your refrigerator at home consumes. So they want more electricity. And we've got another 1.5 billion that use about a third of the level of electricity that Americans use. So electricity globally is going to continue to rise. And even in Europe and the US, as we gravitate to more electric vehicles, and as we move away from combustion powered equipment, our electrical needs will increase. And the challenge is that it is not possible. Let me repeat that. It is not possible to replace our current electrical generating capacity that we have today and grow it in the way that we need with solar and wind. They are a part of the solution, but they cannot be the only solution. Otherwise, we're going to put ourselves in a situation where we don't have electricity security, we don't have food security, we don't have military security, and we don't have economic security. And so as you manage your businesses and your operations, you have to think about how the changing electrical grid, how it directly is impacting your ability to run your operations. So this is a schematic of an electrical grid, and we're going to talk about each of these 4 components just to give you an idea of how this works together. So on the far left, we have the generating station. This is the power plant. The power plant produces the voltage, and then when we connect it to transmission lines, we step it up to a much higher voltage, because power is voltage times current, as you see in the upper left-hand corner. And so in order to transmit that voltage and that current long distances, we basically make the voltage very high. You can see examples there, 765, 500, 345 kilovolts. Now in your home, you're using about 110, 120 volts in the US, and in your plant, you're probably using 480 volts. So these are kilovolts. We're those high transmission power lines that you see that run along highways and through forests. These are incredibly high voltage, and we do that because it allows us to reduce the current. By reducing the current, the conductors and cables in those lines are able to be much smaller, which means we can carry the weight of those cables much greater distances, and we lose the efficiency is better. We lose when current is higher, we tend to lose a lot of that power we're generating just in transmission. Once those transmission lines get to the neighborhood or the industrial park where they need to be, we step that voltage down using a transformer. So the plant uses a transformer to step it up. And then when we get to the substation, we use a transformer to step it down to a more workable voltage. And then that voltage and that current gets distributed to the end users, whether that is an industrial plant, whether that's a commercial facility, or whether that's your home. The important thing to understand is that electricity is generated, transmitted, distributed, and consumed on demand. We cannot store it as inventory. So when you're at home and you flip on the light switch, or you turn on your television, or you turn on your press or your computer at work, there's no communication with the power company. You flip the switch, you turn it on, and that electricity is supplied at the moment you need it in the quantity that you need it. And you can relate to that. Imagine having to fulfill your own customers' orders. As soon as that phone rings, imagine having to produce it, pack it, ship it, deliver it, and consume it as soon as that phone call rings or as soon as that order is placed online. There really aren't many industries that operate under this business model. In the US, we have over 10,000 US power plants that are generating a net 4.38 trillion kilowatt hours in 2021. That is only going to grow. And that has transmitted over 700,000 miles of US transmission lines. And we are about, if I can look at my notes, a good portion of those transmission lines are actually, already at capacity. So we're looking at a grid, right? We're trying to take coal offline. There's pushback against gas. There's pushback against nuclear. The existing plants are aging. The transmission lines are aging. We're trying to replace aging equipment with more renewables that don't perform the same way. So understanding this is incredibly, incredibly important. So let's take a look first at the generating station. So the way power is created at a power plant, it's pretty similar. We use the fuel that we use varies based on the type of plant. This image here is of a coal-fired power plant. So we feed coal in through a chute, and it gets fed into a boiler that you see in the center of the screen. That we burn that coal to generate heat so that we can heat up water and turn it into steam. That steam is carried over to a turbine. So the turbine is the one consistent aspect of all of the different generating plants, with the exception of a solar panel. All of the generating plants, whether it's wind or hydro or coal or gas or nuclear, have a turbine. And we use that steam to turn the turbine. The turbine is connected by its shaft to a rotor, and on that rotor are several magnets. Each magnet has a positive and negative pole. As that turbine spins, the magnets on the rotor spin. And as they spin, they're moving past a series of coils. And by generating a magnetic field, we induce a voltage in that coil. So regardless of the fuel, the idea is to spin a turbine that spins a rotor with magnets. And as those magnets pass in front of those conductors, we're generating a voltage potential. We then step that voltage up with a transformer to a higher voltage, and then it's connected to loads across the grid and current flows. Voltage and current, as you see in that upper left-hand corner, are what we call, it's this AC voltage. It has a sinusoidal formation, right? So the voltage and the current move like a wave. In the US and North America, we use 60 hertz. So you're gonna have 60 cycles per second. In Europe and other parts of the world, they'll operate on 50 hertz. So by changing and maintaining the proper rotation of that turbine and that rotor and the magnets, as well as the number of magnets, we can control that frequency and make it stable, and also control the level of that voltage and produce electricity very consistently throughout the grid. So in terms of the US, about 82% of our electricity generation comes from non-renewables. We can classify those as hydrocarbons and non-hydrocarbons. Hydrocarbons are going to be coal, which make up about 23% of the energy that we use to burn to spin the turbine and then spin the rotor and produce electricity. The coal is brought in by freight, typically by rail. The coal is a stored quantity of energy that we burn. The gases that come off and exhaust through that stack will have various greenhouse gases. The largest one is carbon dioxide, which is why everybody gets focused on the carbon dioxide part of it, is because it's the largest one that we can measure as emission. There's other gases in there that we're concerned about, but carbon dioxide is the one that everybody talks about being the most critical, and we talk about being carbon free because a lot of these fuels, these hydrocarbons, have carbon in them. And so the push to be carbon neutral is to get off of hydrocarbons. Natural gas is delivered by pipeline to the plant, where it then is burned, and you heat that steam to turn the turbine. The same process happens. It's about 38% natural gas in the US. We don't use a lot of petroleum. Petroleum in the center, think about this as you would an aircraft engine, right? This is a combustion engine. We're gonna burn petroleum inside that generator in much the same way an aircraft would burn its fuel for flight. These are the least efficient, the noisiest, and the dirtiest. So we've moved away over the years away from petroleum. You'll find many rural areas, maybe isolated islands or parts of continents that don't have access to a grid. You'll find the petroleum generators, diesel generators are much more common. Nuclear is also considered non-renewable, although it doesn't have any carbon. We're basically using a fission process to split uranium atoms. And when we split those atoms, they release heat. That heat then is captured. It's used to boil water, which then turns to steam. We use the steam to turn the turbine and produce power in the same way as the others. We have not built a new nuclear power plant, or at least ordered a new nuclear power plant in the US since 1975. We've made it very difficult to build power plants, almost nuclear power plants. In fact, it's almost criminal to build power plants. There is some new interest in small modular nuclear reactors. Think about a submarine, how a submarine uses a nuclear reactor for propulsion. We can build small nuclear plants that we can transport on the back of a semi-truck and move it into places that might need energy on demand. There are some power utilities that are doing this, but it's not commonplace, and it's a source of increasing development and research. In terms of renewable is anything that uses air or water or wind, things that by using them, you're not destroying them. So geothermal on the far left, most of the geothermal plants in the US are located in California. We don't use a lot of geothermal. It's location dependent. Not every area can pull geothermal from the ground. We also have hydropower. So this could be a dam on the left or pumped storage on the right. Most people aren't familiar with pumped hydro. It's quite fascinating. You basically have two reservoirs of water at different levels. And during the day when you have higher demand, the top reservoir will drain through pipes to turn a turbine, which then spins the rotor to generate electricity. And then in the evening and at night, when demand is less, they'll use the same energy generated by that plant, that facility, to then pump the water back up to the higher level. Biomass on the bottom left would be burning plant materials. So it would be wood or, ethanol or different things that are basically biodegradable. Solar in the center is about 1.8%. I'm sure you probably thought it was greater, but it's only 1.8% of the solar power in the US, growing, but still a small portion. It's the only one that does not use a turbine. It's the opposite of an LED system. In other words, we use solar panels to absorb ultraviolet light. And as we absorb those into the electrical device, it gets turned in through the PN junction, turns into electrons, DC power, that then travels onto the grid. And on the far right, we have wind, which is effectively a turbine that is spun directly by the wind. So these are the renewables. They're about 17% in the US. The biggest portion really is hydro. And there's pushback now not to build any more hydro facilities. The green environmental movement does not like impact, and so there is pushback against any further hydro facilities. When you look at countries around the world that claim that they are, at 100% renewables or nearing 100% renewables, they do have solar and wind, but by far the biggest portion of that renewable energy that they have is hydropower. So we need to talk about load terminology. And this is, if you're not familiar with this is going to be one of the most important slides that we go over today. So we have base load, intermediate base load, and peak load. So if I look at that image on the right, and I look at my power is along the y-axis and time is along the x-axis. So the base load is the blue shading at the bottom. It's steady, it's constant. It's the minimum amount of electrical generation that we must supply 24/7 at a steady state. We don't like it to vary. We build large generating plants, typically coal, nuclear, and natural gas. And these are big plants and they do the same thing every day. They're very predictable, and they're very steady. We'll use hydro and geothermal when available, and there's an increasing shift to natural gas as we pull back from coal and aren't investing in nuclear. As the day goes on, or as the seasons go on and change, your demand varies. And so at night when people are sleeping, demand is less, but as we wake up during the day and people start turning on their electronics and they go to their production facilities and they start turning on equipment, that demand that we pull off the grid increases. And so this is where renewables such as solar and wind work best, because the sun is out during the day. We can use that intermediate base load from solar and wind to reduce our base load a bit. Peak load is where we have the challenge, right? So this is what you see in California and Texas during the summer. This is what we're starting to see, problems in Germany and Europe. Peak load is a bit unpredictable, right? Because the power plants are not monitoring and talking to you and understanding how you're going to run your production facilities on a daily basis, how you're going to run your air conditioners in the summer, when you're going to plug in your electric vehicle. They have to guess. And so peak load has to be very responsive. Solar and wind are not responsive. They're not even that reliable. So peak load traditionally has been natural gas or petroleum, because both of those two fuels we can turn on and off as needed to keep the grid stable, to keep the frequency stable, to keep the voltage stable, which is very important to making sure that your equipment operates correctly and has a long useful life. So now let's talk a little bit about transmission. Again, we come out of the generating plant, we step up with a transformer to a higher voltage, and we transmit those currents along the line. Current flows when we connect a load. Load being a piece of equipment, electrical device, anything that is connected to the grid that requires power. So in the continental North America, so primarily the US and Canada, a bit of Mexico's connected, but it's really just continental US and Canada. We have 4 grids. We have the Western grid you see on the teal on the left. Texas is basically its own independent grid. And then we have most of the Midwest and the East Coast. And then Quebec is on its own grid as well. So the grids kind of expanded and pooled together to improve reliability. Once you generate electricity, it has to go somewhere. We can't store it, right? So as you made the grids bigger, it gave more routes of transmission for electricity to flow, and that electricity would find the equipment as soon as it was switched on. And it allows the generators, the people that are producing that plant, to supply electricity to many load centers, right? If you're going to build a big, natural gas plant or a large nuclear plant, you want to make sure that the load is there so that you can justify. It's a business analysis, right? You have to justify that the cost and expense to build that facility, which can be hundreds of millions of dollars, can be paid back by enough customers. So as these grids pooled together, we ended up with 4 grids in North America. Those grids also help prevent interruption in service, which makes our grid incredibly reliable. When the electrical industry was deregulated, the independent service operators kind of came into play. You can see an image of the California ISO on the top right. It's basically command center, right? These are nonprofits, non-governmental organizations. They were created to monitor the grid. So you have all these different plants generating power. In years past, kind of in the early days, they were all public utilities that were vertically integrated, right? So if you're a vertically integrated utility, you were managing all of that self as your own utility. As we deregulated the market, as the grids, expanded, you needed an independent set of eyes on the grid. So the ISOs are the ones that kind of monitor where demand is coming from. They will institute brownouts. A brownout is where you lower the voltage. You don't actually cut power, but you lower the voltage. Blackouts are where all the power is cut. So the ISOs are the ones that will kind of roll these into play. They'll spread it around so not everybody is affected at the same time. But they really are responsible for coordinating real-time electricity flow. And they were instituted to ensure fair competition, transparent pricing. And so as you get letters in the mail from different providers and you want to make sure that the information you're being communicated is fair and transparent, right? So that there's no surprises when you open that electrical bill each month. So let's talk a little bit about distribution. So Once we transmit the power to the substation, so substations you see on the side of roads, on the side of railroads, on the sides of industrial complexes, maybe even on the side of a large manufacturing facility, we step that power down to voltages that are more manageable. And then using transformers, we then step that power off and down once again, either to an industrial facility that might need 480, a commercial facility that might need 220, and then an end user that might need 120 or 240. So here's a series of transformers. The image on the top left is going to be a substation step-down transformer and supporting equipment. The image in the center is going to be a pad mount services transformer. You might see these in residential communities or in more commercial areas. You have pole mount service transformers that you see on the far right. Now that you're seeing this image, you're going to see these, you're going to recognize these when you look at a utility pole. That image is of 3 phases, so there's 1 transformer per phase. So if you have 3-phase power, these pole mount transformers would then supply that to your plant. It's important to understand because we don't necessarily always think about it in the US, but I know when we talk to customers in Latin America, it's often, you know, the issue is often raised that they don't have the ability to pull more power off the line, right? Those transformers have a rating, a max power rating. And once your plant exceeds the power coming into your facility, you either need to add another transformer and work with the utility to put that transformer on the line. Now, if the grid and the plant that's supplying that line doesn't have the excess capacity, it becomes very difficult. So we see this in Latin America and we see this in California. And if you think this is not coming to the Midwest and the East Coast, then you need to start paying attention, because we've had the benefit and the luxury of being able to have power on demand and add power as our production facilities grow. As we shift more and more to solar and wind, this is not a guarantee. We're going to be looking at more brownouts, more blackouts, more expensive electricity, and the inability to expand presses as your customer base, as your sales revenue requires. The image in the bottom is of an in-plant transformer. You'll often see these sitting alongside your production facilities. Once we bring the power at the voltage into the plant, we often need to change that voltage. We either step it down to a lower voltage, maybe from 480 to 460, or we'll step it up from 440 to 460. So the final part, which is equally as important, is consumption. So we're going to talk a little bit about how manufacturing plants, as well as commercial facilities and end users, consume the electricity and how we are billed. So anytime that you turn on a piece of electrical equipment, it doesn't matter if it is an air conditioner, if it is the UV on your printing press, if it is a manufacturing line, if it is a motor, it does not matter what that device is. It could be your smartphone. When you turn a piece of electrical equipment on, massive amounts of power rush into that device for a fraction of a second. We call this demand, and we call the highest amount the peak demand. The peak demand and the demand is what necessitates the need to build additional generating capacity. And we're not talking about it in the industry. We talk about consumption, but demand is incredibly important. Because when you turn on electrical equipment, particularly on a Monday morning, after being off all weekend in your production facility, if you're turning all that equipment on at the same time, there's a massive amount of current that's flowing through that transformer into your facility. And the electric companies are watching that, and you get billed for that. They monitor it for usually a 15 or a 30 or 60-minute increments, and they will charge you for the highest values that they see, because you're basically telling them that they don't know when you're going to switch that on. It could be Monday at 8, it could be Thursday at 2, but they have to have enough generating capacity to be able to supply that at the moment in time that you need it. Peak demand charges make up a significant amount of commercial industrial electric bills, and they vary based on the rate structure. You won't necessarily see this in a residential setting in the US, but you will see it in your plant. And it is not uncommon for a large manufacturing facility to have peak demand charges make up about 40% of the electricity bill. And I can tell you that when I sit with potential customers or users in a conference room and I ask them what their peak demand charges are, I would say over 90% one, don't know what I'm talking about, and two, can't answer the question. So a significant part of your electricity bill is not even on the radar of manufacturing facilities. So let's compare power versus energy. So power is demand. Power is demand in the sense that it's a rate. It's the rate of energy delivery. We talk about it in terms of kilowatt hours per hour, but because the hour per hour cancel out, it's basically kilowatts, where a watt is a joule per second. So power is the rate that we are delivering the energy, the electricity to a facility. You'll hear terms like peak demand, peak load, and on peak. Energy consumption is that power over time. It's kilowatt hours. This is what most people are familiar with because it's basic grade school math. You take your cost is the power of consumption times time times your dollar per kilowatt hour. And the way to think about this is the generating plant creates the voltage. You connect the load, which is your manufacturing equipment. When you connect the load, current flows. Voltage times current is power, and power over time is energy. So let's look at manufacturer A and manufacturer B. So manufacturer A on the left pulls 24 kilowatts of power for 1 hour. 24 kilowatts times 1 hour is 24 kilowatts of energy consumption. Manufacturer B on the right pulls 1 kilowatt of power for 24 hours. He also consumes 24 kilowatt hours of energy consumption. So from a mathematical perspective, 24 kilowatt hours is 24 kilowatt hours. They are the exact same. But we'll do a short little pop quiz for those of you that are paying attention. Which scenario do electricity providers prefer, A or B? Well, in this case, it's going to be B because B is easy to predict. B are your customers that order at the same time every month in the same quantities, give you plenty of lead time, and allow you to ship everything ground. A is going to be your customers that call at 3 p.m. on a Friday with an order for something that you never keep on the shelf that you're not even sure you can fulfill, and they want it shipped next day for Saturday morning delivery. You know, who would you rather serve? I mean, a customer that gives you the order frequency of a B or an A? And effectively, the electricity companies are indifferent. We're their customers, and they prefer steady, stable electricity consumption. So as a result, who pays more for their electricity, A or B? In this case, it's A. And this is where peak demand factors in. The more power you pull in the shortest amount of time can affect your utility bills as much as 40%. And it's something that few of us pay attention to. So sustainability initiatives, we're hearing more about this when we attend conferences. Your vendors are talking about it, how they're becoming sustainable. Your customers are asking how you're sustainable. Net zero is a term. Carbon neutrality is what's being thrown around. Originally, net zero was meant to be that you put solar and wind, renewable energy on your property. And so you were generating your own power, and if that power wasn't generating, you either weren't running or you would then have to pull power off the grid. If you were generating more power than you needed, you could sell that back to the grid. So that's really where net zero came from. It's changed a little bit. If we look at the schematic or the image on the left, you're supposed to assess all your CO2 generating areas, right? Whether that's electricity, whether it's heat, whether it's transportation, you're supposed to assess that and come up with a value. If you have renewables on site, wind or solar, you can offset what you're pulling off the grid by generating your own. If you don't have the means to do that, you have to then go and offset that carbon elsewhere by planting trees, by purchasing renewable solar and wind power from your utility at a premium, mind you. And then you can say, if you've done all the math, that you are carbon neutral. There's no perfect definition for this, and the goalposts are changing every year. I show embodied energy at the top of the screen. Embodied energy is not just, looking at how you're consuming electricity in your plant. It's the embodied energy in everything that you're using, which is why your customers are asking for your net zero and your carbon footprint, because they have to calculate that embodied energy in everything that they're doing. The embodied energy of solar and wind is not that great. The materials that get mined, they're built typically in China and then transported to the US. So embodied energy, you're going to start hearing a lot more about, and it makes it even more difficult, and in some cases near impossible for all of us to become net zero. And the targets for net zero are often, 2030 we hear, we often hear 2050. This is a lot more challenging, and there's a lot of greenwashing going on where people are claiming to be net zero when in fact, when you boil down to what their math is, they really aren't. And you need to be cautious. If you're net zero already, you're ahead of the game, but make sure you understand how you're net zero and how you are able to communicate that, because you're starting to see lawsuits, particularly against advertising and PR firms that are talking up companies that really aren't net zero as if they are. And so in the US, we're a very sue happy state. So you just want to do your due diligence and make sure that the reasons you are claiming net zero are indeed accurate and backed up. So equivalence is what we're hearing about. So if you can't do solar and wind on your own property, you have to go buy solar and wind from elsewhere on the grid. And that may not even be in your state. It could be in another state, another region. And so you buy these credits or you pay a premium with your utility so that you can say that when you run your printing press or your manufacturing line, that you're net zero because you are only using solar and wind. The challenge is that you're pulling power from your nearest power plant, right? So all of that electricity flows onto the grid. And on the right-hand side, you can see that same electricity, it's all mixed up, electrons are electrons, and they flow to either the average user or the so-called green user. It's the same power. So this is why if you are net zero today, and we hear this a lot, we'll often hear, well, I'm already net zero. Adding LED does not lower my carbon footprint. And that's simply not true, as you can see here. If you are already net zero, adding LED will reduce the amount of energy you're pulling, and it will allow you to further lower your electricity bills. So what's happening? The electricity companies we're their customers, right? So if you're telling your utility that you only want to buy solar and wind, what do you think they're building? They're certainly not building coal power plants. They're not building nuclear because the regulations are so restrictive. And they are building some gas plants, but the bulk of the generating capacity additions in 2022 in the US were almost all solar, a little bit of natural gas, and a little bit of wind. So we are making our electrical grid increasingly unstable because these sources, while renewable and while advocating that they can deliver a certain amount of generating capacity, wind at its best in the best climate is only about 48% effective at times. Most of the times they're not running, and solar can be as low as 10%. So we're taking coal and natural gas and nuclear that are reliable and on demand, and we're replacing them with solar and wind that just aren't as reliable. Now they need to be part of the solution, and we will continue adding solar and wind, but we have to be careful how quickly we back off of the other hydrocarbons and nuclear materials. These are the projections for 2050. You can see even by 2050, it is not possible for us to be powering our facilities exclusively with renewables. It's going to be a mix of solar, wind, hydro, natural gas, nuclear, and coal. So let's look at some real world examples. In the US, we often hear about California and Texas, and in Europe, we often hear about Germany. California and Germany both dove into this very early, probably 15, 20 years ago for California, and definitely 20 years for Germany. They subsidized the construction of solar and wind, and they created policies that encouraged us to move away from coal, nuclear, natural gas. And so as a result, they have grid problems. It's not uncommon to hear about how there are outages in California, rolling brownouts, rolling blackouts. Texas has come on the scene recently. They've had some extreme weather conditions. It was really, really cold during the winter of 2021, and a lot of their equipment, which is aging because The power generators are not investing in aging equipment. Who wants to dump money into a coal plant? Who wants to dump money into a nuclear plant when these are going to be taken offline? So aging equipment doesn't perform well under stress. And the wind power wasn't running. And so it just created this nightmare that resulted in a lot of people being out of power. And when the power goes out, that takes a toll on your equipment. It's actually better to have a blackout than it is to have a brownout. Running equipment at low voltages can really destroy your equipment. So what's happening? Texas, well, let me talk about California. So California is, Gavin Newsom just passed a bill, signed off on a bill a few weeks ago that basically gives the state the ability to override any pushback from local facilities, because they know they've got to act fast to basically strengthen their grid, because the brownouts and the shortages are just getting worse. Germany went to the G7 in June and basically expressed their desire to start burning more coal because their electricity rates have just skyrocketed. And it's not that anybody wants to move away from solar and wind. They will be part of the mix, but we're doing it way too quickly, and it's driving electricity rates through the roof. I mean, Germany went, it's not, France, in the US, we have a dollar per kilowatt hour of about 11 cents. In France, it's about 23, and in Germany, I think it's well over 36. And we often hear from customers that are paying 50 cents equivalent dollars per kilowatt hour in Europe, and that's not sustainable. I mean, how do you run a business at those prices? I mean, we're doing what we did to the chemical industry by offshoring everything to Asia, by creating an environment where it was just inhospitable. And now we're doing the same thing for energy. Businesses thrive when energy is affordable and reliable and scalable. And when it's not, it finds places where it is. And in China and India, they are building coal and natural gas plants, because coal is, unfortunately, however you want to take the position on this, it is the densest source, one of the densest sources of energy. And that's why they are building coal power plants. So here's another example from, and I just have a few more slides. This is from a printer in Southern California. So they were struggling for years with very high peak demand rates. So they run 5 days a week, 24 hours, Monday through Friday. So on Monday morning, when they come in and they go to switch on, they've got 3 sheet-fed offset presses. And so when they turn those presses on a Monday morning, all of that inrush current floods into their plant, right? And that raises their peak demand, which then is billed as a penalty or as part of their demand rate. So their electricity bills go up significantly because they're switching all of their equipment on at the same time on Monday morning. So what they did is they stagger. They bring guys in earlier, before the peak demand time starts, and they stagger on Monday morning how they bring those 3 presses online. And then they actually went out and bought a Tesla inverter, which is what you see on the right with the Tesla logo, and 3, they call them 2-hour battery packs. Each one of those 3 vertical columns on the left can supply about 174 kilowatt hours. That is not a lot of power. So you can see the size of this, right? I mean, just the side of the building and the transportation, the car blocks, the yellow post that you see there. That's not a lot of power. It helps them get through the demand. So these are smart batteries in the sense that they're connected to the grid. So they charge at night when the rates are low, and they will kick on. They automatically switch on during peak demand hours, so that this plant can pull, 1 or 2 hours off their battery, their Tesla battery and inverter, versus pulling it off the grid. So battery power is not there yet to be able to store wind and solar to the level that we need to run our plants. In fact, there is not a single grid anywhere in the world that is operating exclusively on solar and wind. Again, they're part of the solution, they're part of the mix, but they are not a replacement. So what does this mean? Well, we're stressing the grid. We are definitely stressing the grid. We are pulling away from proven energy and replacing it with less proven and less reliable energy, and that's causing power outages. So the power companies, they need to manage this, right? And so they have 2 choices. They can build more plants, but who wants to invest in coal and nuclear when it's very cost prohibitive to do that? So what they are building, as that previous slide shows you, is they're building solar and wind. But they're also trying to get consumers to use less energy. And this is where the rebates come in. If you are looking at installing LED or looking at installing more efficient equipment, the key thing to tell your electrical provider is that you want to lower your peak demand. That is the key word. It's not consumption. They can manage consumption. What they're struggling to manage is peak demand. Going LED lowers peak demand. Two kind of somewhat technical slides. Please bear with me if you don't have a technical background, but these are incredibly important. We talk about power factor and active and reactive power. And I'm going to go through this fast, and we can always cover this in more detail later. Certain pieces of equipment require active or real power as well as reactive power. Transformers, motors, UV curing systems need a bit of reactive power. If you think of the real or active power as the beer in that pint glass, and the foam at the top as the reactive power, the foam doesn't really benefit us, right? If someone pours you a pint of beer and it's the end of the keg and you get half foam, you're not a happy person, right? You're paying for that pint and they gave you half the beer. It's the same thing with power. Reactive power flows on the line. It is necessary for some equipment, but too much makes the electrical grid inefficient. There is equipment in your facilities that is creating reactive power. And if it's not addressed, it is making everything in your plant, all of your presses, all of your lines, all of your motors, run less efficient. So part of sustainability initiative is understanding what you're generating inside your facility and correcting for that. We calculate power factor by dividing the active power by the apparent power. The best it can be is 1. 0.95 to 1 is very good. Less than 0.95 is bad. And if your plant has a power factor of 0.9 or 0.8 or 0.7, it is costing you more money to run your equipment. You can do power factor correction in your plant, and that will lower your electricity bill. If you don't do it, then the substation has to do it by adding capacitors to the line to balance the inductive loads in your plant. So poor power factor means that the load, your machines, pull more current from the grid to do the same work. And we often specify electrical equipment in that apparent power. We specify our UV curing systems, LED and arc, in terms of the kVA rating. And that is what you will see on our spec sheets and all of our documentation. So it's important to understand what that is. kVA includes active power and reactive power. Just a couple quick slides left. AC loads, and again, another technical slide. I apologize to those of you who aren't technical, but this is important. Resistive loads, inductive loads, and capacitive loads are what you're going to see connected to an AC line. In an ideal world, the resistive load that you see on top, the voltage and the current are in phase. They cross the x-axis, which is time, at the same point in time. This is an efficient circuit, but most equipment is not a resistive load. It's either inductive. Most of them are inductive. Some of them are capacitive. For the inductive load, we can see that the current lags the voltage when crossing the x-axis. So the current, if this is time, so the axis here where the y and the x cross, that's 0. So the voltage is actually crossing 0 first, and then the current crosses, so it lags it. In a capacitive circuit, it's the opposite. So if you can have a resistive load or correct your inductive load so it behaves like a resistive load in your plant, your current requirements and losses are minimized. Your total power required is minimized. That directly hits your electricity bill. Your power losses are minimized. Your total power is your active power, and there's no reactive power. So being greater than a power factor of 95 is sustainable. It frees up capacity on transmission lines, distribution lines, transformers, substation equipment, and it's better at protecting your equipment, life and reliability, and it lowers your bill. So the final slides that everybody's waiting for. What does any of this have to do with LED? Well, going LED from either a thermal dryer, a thermal oven, or a conventional arc lamp or microwave curing lamp to LED will reduce your installed power. So you're pulling less off the transformer. It will reduce your demand. So when you start up on a Monday morning or every morning, you are pulling less current when you flip that equipment on. And it lowers your consumption over time. All three of these will impact your utility bill. So we have 3 comparisons of an arc lamp system, an LED system that's water cooled, and an LED system that is air cooled. This is an example taken from a Flexo press, an 8-station Flexo press. We have the Rhino cabinet, which powers everything on our equipment except for the chiller. So you can see on the left scenario with the mercury arc system, we have 62 kVA for the arc lamp. The LED, we have 32 kVA for the Rhino, and the chiller is 20 kVA. You add them together. And then for an air-cooled LED, that dropped to 27 kVA. Lowering that apparent power from 62 to 52 to 27 is sustainable. This does more for you than buying renewable credits from solar and wind on the line, because this is something you control in your own plant. And it reduces your power in the example on the far right by as much as 66%. And so that translates into energy, right? Power over time is energy. So in a typical year, you're going to pull kilowatt hours as shown on the screen. Going LED reduces your consumption over time. So what does this mean? Couple quick slides. Voltage from the generating station, you add a load, current flows. Voltage and current means power. Power over time is energy. Power is also voltage times current times power factor. Again, get those power factors above 0.95. And then energy is power over time. So what does this also mean? Well, it means if you've got multiple, like my customer I was talking about in California that's got 3 sheet-fed offset presses currently running UV, if you can't pull any more power off your line by moving from a thermal dryer or an arc lamp system to LED, means you're going to lower that current draw so significantly that you can often add another line by not increasing the total current draw or the total power draw. So again, another way to add capacity and also save money. So you need to look at your electricity bill, right? You need to understand how you're metering, how it's being metered, the charges for your demand, your charges for your consumption, what is your power factor, and what is the load factor. I'm not going to talk through the slide, but you need to look at your electricity bill. Pull it out. It's something you can do yet today, something you can do this week. Understand what you're being charged, because LED can help lower all of these charges on your electricity bill. So overall, LED helps sustainability and reduces costs because it reduces total installed power. It reduces peak demand at startup, which is key because that's what drives needing to build new generating plants. It reduces consumption during operation, and it reduces carbon footprint, even if you are already net zero. So a couple action items here. Look at your electric bill, pull it out. If you've never looked at it, or if your management team has never looked at it, if it's just going straight to accounting and it's getting a check's getting written, a wire transfer is happening, you need to understand the components. Confirm your billing rate. Is it going up? Is it changing throughout the course of the day? What is your peak demand and how is that applied to your bill? Are you charged as a penalty or is it built into the consumption rate? What are your AC voltages? Just because the generating plant is providing you with 480 volts, it may be that you're pulling 490 or 500 off the line. If you are, you need an internal step down transformer to make that 460 because you're tearing your equipment up by running at high voltages. What is your power factor? If your power factor is below 0.95, you need to add banks of capacitors to get that up higher. Your electricity bills will go down and your equipment will run better. If you need to commission a plant energy study, contact your electricity provider, contact a third party. It is worth the investment. I talk to customers all the time that do it, and they're surprised what they learn. And then understand the true impact of your net zero policies. Know what they are. Don't just say you're net zero. Understand what you are doing to make yourself net zero. And then investigate rebate incentives. 1 through 8, you can do pretty quickly. And then 9, transition to LED. It will help every aspect of your operation. So closing thoughts, and I'm right at an hour, which means we're not going to have time for questions. But my closing thoughts are we all need to be good global stewards of the environment, right? And there's lots of ways to do that. I go back to the old adage, which has been around for a long time, is think globally, but act locally. Look inside your plant. What can you do? What are you doing already that's basically making the grid inefficient? And what can you improve by making slight changes that will not only improve the grid, but also at the same time lower your electricity costs? So LED delivers a strong ROI primarily because it lowers peak demand. That is key, and it's not something we're talking about enough. So I want to thank everybody for joining us for this webinar. You've got my contact details on the slide. Please don't hesitate to reach out to me. I could have talked about this subject for even several more hours. There's so much good information. You've also got my colleague Amir Deckel. We're both based here in the States. If you want to contact anybody in Europe, please go on our website and all the contact details are provided. So thank you very much.
Jennifer, thank you so much. That was a great presentation, some great information. And as you said, we're really short on time. There was a couple questions, but please feel free to email Jennifer direct. And if you have any questions on LED specifically and about her presentation today, I want to thank Jennifer and GEW for sponsoring this webinar. And we really appreciate your time, and thank you for everybody that was able to join us. We appreciate it. And Jennifer, thank you again, and
Thank
we
you
will
very
talk
much.
soon. All right.
Thank you very much. It's a fascinating topic. Thank you.
It is. Thanks. Bye-bye.
Bye-bye.